Hello student, how are you? I'm Arun sir. Welcome to my channel Tuition Expert. Today's class is on SHM, that is simple harmonic motion. Student, I will finish the whole SHM chapter with derivation and problem in two class. In these two class, all the idea of SHM will be cleared. You don't require to see another video. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the iitjee exam and NEET exam confidently with good rank. Now let's start about the class. Harmonic motion. In simple harmonic motion, first we understand what is periodic motion. What is periodic motion? Second, oscillatory motion, and SHM, that is simple harmonic motion. So what is periodic motion? That is if a particle, suppose a pendulum, you know the pendulum in old type of wall clock, in old wall clock, you know, a SHM, that is oscillate from this to this, that is there is a mean position, and from mean position the bob of the pendulum oscillate, and after every equal interval the particle comes at its same position. Suppose the time period of this pendulum is 2 seconds, so after every 2 seconds the bob comes here, and again after 2 seconds the bob comes here, again after 2 seconds the bob comes here. So after every 2 seconds the bob comes at this position. Suppose your school starts at 8 am every day, so after every 24 hours the school starts, so that is periodic motion. Now what is oscillatory motion and SHM motion? Oscillatory means the particle will oscillate about a mean position. So best example is pendulum. In old wall clock, what is pendulum motion? A mean position is present, in mean position is and about the mean position bob moves left and right equal distance. So this is oscillatory, that is it moves right and again left, right and left about a mean position. So this type of motion is oscillatory motion. Oscillate, that is swings, that is in park swings motion. I will describe what is oscillatory motion and what is SHM by equation by force. If F equal to minus k x to the power n, in this type of force, for what value of n, this is oscillatory motion and this is SHM. So if n equal to odd, if n equal to odd, then the motion is oscillatory. The motion is oscillatory. If n equal to odd, then the motion is oscillatory, because here suppose, so this is oscillatory motion. Here suppose this is mean position, left and right. So this is here this is positive x-axis, and here this is negative axis, negative x-axis. Now if that is when the bob moves in this direction, x is positive, and suppose f equal to minus k x cube, n is odd, s cube. So if the bob is here, that is x is positive, then direction of force is along this direction. So x is in this direction and force in this direction, that is always force is opposite to x. Now here x is negative. If x is negative, then force is positive. Force direction is this. So this type, that is x and f is opposite direction. Okay, suppose x and f and x will be opposite direction. So this is oscillatory motion, pendulum motion. Here is the O is the midpoint, and if the bob moves in this direction, x is positive plus x, and what is the direction of force? Force direction is along in this direction. So f and x is opposite. So if x is positive, f is towards negative. This is negative f towards negative. Now if if the x is negative, when the box move in this direction, that is minus x, then what is the direction of force? Force is plus f. So if you put here x equal to negative, f is positive, minus k minus x cube, which is equal to kx cube. So if it positive, so this type of motion, this is oscillatory motion. So for oscillatory motion, force equation will be f equal to minus kx cube. That is, here n will be odd, then its motion is oscillatory motion. X समान 0 position, 0 is mean position. If the, that is the particle oscillate about the 0 position, Now if the equation is minus k whole cube, so here particle oscillates about the position x equal to 2. So x equal to 2 is mean position. Okay. So in this type of motion, if n is odd, then the motion is oscillatory motion. 3, 5, every odd power denotes the motion is oscillatory motion. Now if particular n equal to 1, then the motion is SHM. If n equal to 1, then f equal to minus kx, then this motion is simple harmonic motion. This is, so for n equal to 1, this will be simple harmonic motion. For SHM and oscillatory motion, what is the common condition? The common condition is that the motion will be periodic. Two common properties: motion will be periodic for oscillatory and SHM. So periodic is the common property of all oscillatory and SHM. It must be periodic. It must be periodic. Okay. And second condition is f is proportional to minus x. That is, acceleration is proportional to minus x. This is the main condition. Periodic motion, periodic is special condition of SHM is that it must be periodic, but also a is proportional to minus x. So this is the main condition. Special condition of SHM is acceleration is proportional to minus x. What is the significance of minus? So acceleration and displacement are always in opposite direction. Okay, check whether so suppose these motions are given, these equations are given, and you have to prove which is simple harmonic motion, which is the equation. You have to prove which are the equation of simple harmonic motion. Okay, you have to prove which are the equation of simple harmonic motion. No, so for one we have to, for SHM we have to prove acceleration is proportional to minus x. We have to prove this. Now for one solution, for one, first we find velocity equal to, dx by dt. Okay, so what is the derivative of this? Sin square omega t, that is 2 sin omega t, and derivative of sin omega t is cos omega t into omega. So this is this, so that is 2 omega sin 4 omega t. So this is sin 2 omega t. So now this is velocity. So acceleration equal to dv by dt. Again, dv by dt means 2 omega into 2 omega cos 2 omega t. That is 4 omega square cos 2 omega t. cos omega t means 1 minus 2 sin square omega t. So 4 omega square 1 minus x, 2 sin square omega t equal to x. Now a equal to this, so a is not directly proportional to minus x, a is not directly proportional to minus x, so we cannot express this in this form, so this is not SHM, so this is not SHM. Next, number 2, not SHM, no, not SHM motion. Number 2, for number 2, x equal to this, so velocity equal to dx by dt, which is equal to 4 into, this is derivative of this is 2 pi cos 2 pi t, this is velocity, and acceleration equal to dv by dt, which is equal to 8 pi into 2 pi sin 2 pi t. Now derivative of cos is minus, so this is minus square sin 2 omega 2 pi t. Now 4 pi square into 4 sin 2 pi t, okay, 4 sin 2 pi t. Now 4 sin 2 pi t equal to x, so a equal to, here a equal to minus x, a is proportional to minus x, so this is SHM, so this is SHM, okay, so this motion is SHM. Now for 3, dx by dt, velocity equal to dx by dt, which is equal to pi sec square pi t, and a equal to dv by dt, which is equal to pi into 2 sec pi t into derivative of sec is sec pi t. Now by chain rule method, I differentiate both sides. By chain rule method. So sec square theta equal to 2 sec theta into derivative of sec theta equal to sec theta tan theta into again pi again. So this is the acceleration. So we cannot express in terms of x here. X equal to tan pi t. So a is not proportional to x. A is not proportional to minus x. So this is not SHM. This is not SHM. Next, 4 cos pi t. Number 4, velocity equal to dx by dt, which is equal to 4 pi minus 4 pi sin pi t, and acceleration equal to dv by dt minus 4 pi into pi cos pi t, which is equal to cos pi t, that is minus pi square 4 cos pi t equal to x. So a is proportional to minus x. So this is SHM. This is SHM. A is proportional for 4. This is A is proportional to minus x. So this is SHM. Now for 5. Now for 5, x equal to this. V equal to dx by dt. dx by dt equal to 3 omega cos omega t minus 4 omega sin omega t. Now acceleration equal to dv by dt. So this equal to 3 minus 3 omega square sin omega t minus 4 omega into omega cos omega t. Okay. So this equal to minus omega square 3 sin omega t plus 4 cos omega t equal to minus omega square into x. So a equal to minus omega square x. This is proved. So here a is proportional to minus x. That is number 5 is SHM. So this is SHM equation. So this is SHM. Okay. Displacement equation of SHM. Displacement equation of SHM. So to express that displacement equation, we have to relate some angular motion and linear motion. Angular motion and linear motion. Because we know that SHM is type of oscillatory motion. The type of oscillatory motion, to and fro motion, and special case is A is proportional to minus x. That is, this is linear. Linear in a straight line, to and fro motion. We know this is SHM motion. But we express displacement equation is as x equal to a sin omega t or a cos omega t, or when there is initial phase a sin omega t plus minus phi, etc. So here omega is related for angular velocity, that is in circular motion, and but we know that SHM is linear type of motion. We are familiar with the linear type of SHM, but when we express displacement equation, here a angular velocity is present. Now what is the relation between angular motion to linear motion? What is the relation between angular motion to linear motion? We have to relate the angular motion to linear motion by simple example. How circular motion is related to linear motion, I will describe by simple arrangement. Suppose cylinder piston in automobile engine, the cylinder piston moves linearly. Cylinder piston, this is piston, this is cylinder. So piston moves in the cylinder up and down this way. But here so by this type of arrangement, piston moves up and down, but wheel of the car rotates in a circular way. So if this motion accelerates, then this motion also will be accelerated. If the motion stops, this will be stopped. So this is linearly moved, but this is in circular motion. So this way, this linear motion is converted to circular motion. That is, so there is a relation between angular motion to linear motion. Now for each linear motion, there will be a corresponding angular motion. We can convert linear motion into angular motion by suitable mechanism. We can convert linear motion to a angular motion by suitable mechanism. So in industry, in mechanics, every linear motion in every linear SHM can be converted to angular motion. So when we express x equal to a sin omega t plus theta phi, then this is omega is always related to angular motion, but x is related to linear motion. So now I can, so displacement equation of SHM, suppose a particle rotates in a circular path. A particle rotates in a circular path. Suppose a particle rotates in a circular path. Now the diameter, suppose this is the diameter of the circle. Now the particle is here. So suppose the particle rotates in a circular path. Now if we draw the perpendicular on the diameter from every particular position of the particle, suppose we draw perpendicular. Now we draw the perpendicular. Now foot of the perpendicular moves in this direction. When the particle comes from this to this, the foot moves in this direction, foot moves in this direction, particle comes from this to this position, and automatically the foot shift in this way. When the particle moves in this direction, again foot comes in this way. So here now when the particle move in circular motion, particle which is in circular motion moves from this to this, then the foot of the perpendicular moves from this to this, foot of the perpendicular shift from this to this, and again when the particle moves in this direction, then the foot moves in this direction. So the particle which is in circular motion describe the circular motion in this way. Now the foot of the perpendicular on the diameter, foot of the perpendicular on the diameter describes the SHM. Okay, you can understand. This is very important. How circular motion is related to SHM. Here particle describes the circular motion, but its foot of the perpendicular on the diameter, but its foots of the perpendicular on the diameter describes the SHM. When the particle stops, the foot will also be. When the particle increases its speed, velocity of the foot correspondingly increases. Suppose the foot of the perpendicular moves in this direction. Suppose the particle moves from this position to this position and describe a angle theta. Now foot is here and foot moves the x displacement from the mean position. This is the mean position O. From this the here amplitude is A. Amplitude is the radius of the sun. What is amplitude? Amplitude is the maximum distance moved left and right, left and or right. Maximum distance moved left or right from the mean position is the amplitude. Okay. Now suppose the foot is at here from the at a distance x from the mean position. Now if this angle is theta, this is theta. So O, suppose this angle is this is P. So from triangle OPN, what is sin theta? Sin theta equal to x by a. Sin theta equal to x by a. So x equal to a sin theta. X equal to a sin theta. Now what is if the particle rotates with angular velocity omega? Now we know that omega equal to theta by t. So theta equal to omega t. So we put here omega t. So this is the equation of SHM. This is the displacement equation of SHM. Now this equation we write when the particle starts from mean position. When the particle starts from mean position, from this position, the particle rotates from this to in this direction clockwise, and the foot of the perpendicular which describes the SHM, the foot starts from the mean position. So when the particle starts from mean position, we use this equation. Okay. Now here at t equal to 0, phase angle, that is omega t equal to 0, that is x equal to 0. So t equal to 0 means x equal to 0. A is the, what is A? A is the amplitude. What is A? A is radius of the circle or amplitude of SHM. Amplitude of SHM. So this is the displacement equation. Now what is the suppose the particle starts from here. That is initially particle starts from not mean position. This is origin. This is minus x. So angular position is the left to the vertical line. Left to the vertical line. The particle starts from here. Now when it moves from this to this, here comes. Now its foot is at here. So foot is at here. Now we have to find this angle is theta. Now we have to find this angle. This angle will be theta minus phi. So this angle will be theta minus phi. theta minus phi. Now from OPN, from triangle OPN, sine theta minus phi equal to x by, this is x, this is x, this is initial position, suppose minus a distance, suppose minus b. We express this as x, sine theta minus phi equal to x by a is amplitude of the SHM, so x equal to a sine theta minus phi, which is a sine theta equal to what? Theta equal to omega t, we know, put here omega t minus phi. So this also a equation of SHM, where now this angle is called omega t minus phi is a phase. This is called phase. Angle is called phase. Phase is the angle from this angle we can understand, we can know, from this angle we can know what is the initial position of the particle. So if t equal to 0, then what is this angle? The angle is minus phi. So at t equal to 0, the angle will be minus phi. Minus phi means that is left to the particle. So this is the initial phase. This is called initial phase or epoch, minus phi. Initial phase or epoch. So t equal to, at t equal to 0, this is the phase is minus phi. Put here t equal to 0, the angle is minus phi. Minus phi called initial phase or epoch. Now if the particle starts from here, this to this, and comes here, so this angle is phi, this angle is theta, and we have to find this angle. This angle will be theta plus phi, this angle will be theta plus phi. This is a, this is x. So again we know sine theta plus phi equal to x by a. So x equal to a sine omega t plus phi, So this is the displacement equation. So at t equal to 0, what is initial phase? Initial phase or epoch equal to omega t, which is positive. So phi, initial phase is phi. So phi means positive phi, that is right to the vertical line. That is here particle starts. Here particle start. From this particle starts. So when x equal to this, we know that particle starts from the right, from the vertical side. The particle rotates in circular path from this position, this angle, from this side. Now the particle starts from this. Suppose the particle is at here, at t second, in t second the particle is at here and makes an angle theta. So its foot is here, this is origin, so this distance is x, this is the amplitude a. Now here theta equal to omega t, so OPN. Now from triangle OPN, what is cos theta equal to x by a cos theta, x equal to a cos theta, so a cos omega t. So x equal to a cos omega t, x equal to a cos omega t. This is the equation of SHM. This is the displacement equation of SHM when the particle starts from extreme position. So we use this equation a cos omega t when the particle starts from extreme position. Okay, t equal to 0 at here. So particle starts from extreme position, this position. Particle starts when the particle which is in circular motion is at here, and the particle which describes the SHM, this also is at here. So foot that is n is also at here. Now the particle which is in SHM moves in this direction and the foot comes in this direction. So here the SHM, the particle which is in SHM or which performs the SHM starts from the extreme position. Now we always, so this is important point, we always this displacement x, x is measured always, x is measured from mean position always. This is important points. X is measured from mean position. The particle starts from mean position, whether the particle starts from mean position or from extreme position, but we always we always measure the x from the mean position. Okay, we always measure the x from the mean position, whether the particle starts from extreme position or the particle starts from the mean position, but we always the distance x from the mean position. So in displacement equation, x is always measured in the mean position. I repeat the once again the theory. In displacement equation, the distance, that is x equal to a sin omega t or x equal to a cos omega t. This x is always measured from mean position. When we use this equation, when the particle which is in circular motion starts from the mean position, the particle which is in circular or the particle which is in SHM, both will start from mean position. Then we use this equation, and when the particle or particle which is in circular motion or the particle which is in SHM, both will start from extreme position. Then we use this equation from up to the horizontal line at an angle phi up to the horizontal line. Then we use this equation. So this is the omega t is the extreme when the particle starts from extreme position, and this when the particle starts left down to the horizontal, then we use this equation. When the particles start up to the horizontal line at an angle phi up to the horizontal, we use this equation. Why? So if the particle starts, if a particle starts in circular motion, and if we take the displacement along y-axis, so this is displacement. So particle starts from here. The particle which is in circular motion starts from here. So this is the mean position, and along this is the mean position. Origin is the mean position. When the particles moves, when the particle which is in circular motion moves from this to this, then an angle next is theta. So here foot, if you draw the foot on the y-axis, so this is the foot. So this will be the displacement. Y is the displacement. So this is y, and this is amplitude A. Now if this angle is theta, this angle is theta. So from the triangle OPN, here the triangle OPN, we can show cos sin theta equal to y by sin theta equal to this is base angle, base perpendicular hypotenuse, y by a. So y equal to a sin theta, a sin omega t. So we can show in different way. If the displacement is in terms of y, then we can show in this way. So y equal to a sin omega t also with the equation. So if we express the displacement in terms of in y, then we have to start from here. The particle which discussed in circular motion starts from this position. So this is the mean position, and if the particle rotates, then the foot also rotates along y direction. So we take y is the displacement equation. We take y for displacement equation of SHM, velocity equation of SHM. Suppose the particle is at here, and the particle moves from this position. We always describe the motion of two particles. But one is motion of one particle is circular motion. Motion of one particle is circular, and motion of its foot of perpendicular on diameter is SHM. So when I repeat circular motion which is in SHM, so we always describe two motion, circular motion is circular and motion of its foot of perpendicular on diameter is SHM. So here suppose the particle which is in circular starts from here and it describes in circular motion and its foot of the perpendicular, that is N, this describe the SHM along the diameter. Okay, I have described in displacement equation also in details. Now suppose the particles which is in circular motion moves from this to this. Here the velocity of the particle, we know the velocity of the particle in circular motion is always along the tangent. This is the velocity of the particle is in this direction. Now the foot, when the particle reach at here, the foot is at here, foot is at here. Now what is the velocity of the foot? Velocity of the foot is in this direction, v. Now this velocity comes from this velocity actually, because a projection, a part, a component of this velocity along this direction provides the velocity of the foot, So a component of this, if this angle is theta, then this is theta and this angle is 90 minus theta, because this and this is perpendicular, and also this and this, is 90 degree, and the 90 degree, this is 90 minus theta, so this angle is theta. Now what is the component of the velocity along this direction? This component will be v cos theta. Okay, the component of this along this direction is v cos theta. So this will be the velocity of the particle which is in SHM. So velocity of particle which under SHM will be v cos theta. Now what is the v? If the particle is in which is in circular motion rotates with angular velocity omega, and a is the amplitude of the particle, so v equal to omega a, and theta also omega t, so v equal to omega a cos omega t. So this is the equation of velocity, this is the velocity equation of SHM in terms of time. Also we express this in terms of x. Now we know that x equal to, this is x equal to what? X equal to a sin omega t. We know that x equal to a sin omega t. So put here omega a into root over cos omega t equal to what? Cos omega t equal to 1 minus sin square omega t, which is equal to 1 minus sin omega t. Sin omega t equal to what? Here sin omega t equal to x by a. So put here this, so omega a into a square minus x square 1 by a cancel, so v equal to this. So v equal to this. Now this is the velocity expression. This is the velocity expression. You student remember this formula in terms of x, and this formula in terms of time. If that so two formula, velocity formula in terms of time, this is in terms of x, in terms of displacement. Velocity maximum will be omega into a when x equal to 0. That is, we know that when a particle performs SHM this way, suppose take the case of pendulum. When the pendulum is at mean position, then its velocity is maximum. So x equal to 0 represents the mean position. So when x equal to 0, velocity maximum, and maximum velocity is omega a. So this is a formula. You remember this is as formula, maximum velocity equal to omega a, and when x equal to a, that is at amplitude, x equal to 0 means mean position, and x equal to a means extreme position. So when x equal to a, v will be minimum, minimum velocity will be 0, because if we put x equal to a, then we get the minimum 0. Acceleration equation of SHM. Acceleration equation of SHM. Now, suppose this is particular this that here, this diameter, this. So at equal to 0, particle is at here, and it describes an angle theta, which is in circular motion, and its foot is here. Foot is here, foot of the particle along the diameter. We know that foot describes the SHM, and this particle describes the circular motion. So theta. Now this is the x. This is the x. Now in circular motion, what is the acceleration of the particle? The particle rotates with angular velocity. Omega is uniform. Omega uniform angular velocity. Uniform angular velocity. So if the particle rotates in uniformly, then its tangential acceleration, then its tangential acceleration is 0. But there is a normal acceleration which is value omega square r. Here r is a. We take this r is a. So normal acceleration omega square. Now what is the direction of normal acceleration? What is the direction of normal acceleration? Direction of normal acceleration is along. So this is the normal acceleration. Now what is the acceleration of this particle? The component of this acceleration along this. We have to, now we can resolve this value along these two directions, this and this. Now the component of this along this direction will be the acceleration of the particle. Okay, component of this n along the horizontal direction will be the acceleration of the particle n. So acceleration of particle n, that is under, which is under SHM. SHM will be an. Now if this angle is theta, this angle is theta, and this angle will be, this is, so an, this component cos theta, and this component will be sin theta, n sin theta. So an sin theta, n sin theta. Now what is an? An equal to omega square a sin theta. Now is the force is along this direction, so we put here negative. Now we know x equal to a sin theta or a sin omega t is the displacement equation, so minus omega square x. So acceleration, the formula of acceleration of SHM is this and this. So this is the in terms of theta or omega t. This is the in terms of time, and this is in terms of displacement. So acceleration, what is the formula of acceleration of SHM? This and this. Acceleration a maximum equal to omega square into a. We take the magnitude value, that is we take the magnitude, not sign. Maximum acceleration equal to omega square when x equal to a, and minimum acceleration equal to 0 when x equal to 0. So acceleration is minimum at mean position, and this is at extreme position. This is opposite of velocity. At extreme position velocity is 0, velocity becomes 0, but acceleration is maximum. At mean position velocity was maximum, but here acceleration is minimum. Force on a particle under SHM. So force equal to just mass into acceleration. Acceleration is omega square. So force is variable force. Just to remember force, the formula of force is m omega square. Maximum force is m omega square a, and minimum force equal to 0. Maximum force acts at extreme position, at maximum force acts at extreme position, and minimum force at mean position. Energy of SHM, energy of particle under SHM, energy of particle Now suppose a particle executes SHM from the mean position. Suppose the particle is at here, the particle is at distance x from the mean position. Total A is the amplitude of the particle. Now here, due to velocity, a kinetic energy is present. So here, due to velocity, the particle possesses some kinetic energy, and also it moves. So kinetic energy of particle equal to energy possessed by its velocity, which is half mv square equal to omega square into s square minus x square. So this is the kinetic energy. Kinetic energy of the particle will be this, but due to what is the potential energy? Potential energy means what done in bringing the particle from mean position to that position. What done on the particle from in bringing the mean position to that position, in bringing a particle from mean to that position. The force acts on this particle in this direction. So the particle moves against the force this. So a work has to be done to move the particle. A work has to be done in bringing the particle against the force. So now the work done is for variable force. What is the work done in variable force? Work done in variable force is equal to f dx, and it brings x is varies from 0 to x. Suppose now what is f? F is at x position is m omega square x dx 0 to x. So this is m omega square. Now what is the variable x dx? X dx is x square by 2. If we put the integral, we get half m omega square x square, upper limit x and lower limit 0. So we get this. So this is the formula of potential energy, because we know what done on a particle is the potential energy of the particle. So potential energy we get half m omega square x square. Energy graph. This is the displacement x, this is the energy, the origin, and this is A. So this is the energy graph. We know what is the formula? Potential energy, kinetic energy formula is right here. Kinetic energy formula is half m omega square a square minus x square. Potential energy is half m omega square x square, and total energy equal to half m omega square a square. So we get three energy, this and this. Now at x equal to 0, what energy 0? Potential energy 0. So at x equal to 0, potential energy 0. So this will be the potential energy graph. This is the potential energy graph. This graph. X equal to 0, potential energy 0, and if x increases, potential energy increases. So at this is the amplitude at A. Okay, now this is the graph of so at x equal to a, the potential energy at x equal to a potential energy is maximum. So this is the potential energy graph, and x equal to 0 potential at x equal to 0 kinetic energy. This graph kinetic energy is maximum, so this graph is this graph is kinetic energy graph. This graph is kinetic energy. This is kinetic energy graph. Kinetic energy graph, and total energy is independent of x. Total energy is independent of x. So this is the total energy graph. Total energy graph. So three type of graph we present. We got three graphs, graph of three energy. Now what is this point where kinetic energy and potential energy equal? What is the 2 point? We get 2 point on x-axis where kinetic energy and potential energy equal. So for that we get to get this distance, we equate kinetic energy. We equate kinetic energy and potential energy, equating kinetic energy and potential energy. Cancel this. We get 2x square equal to a square. So ax equal to a by root 2 plus minus. So at 2 position we get the potential energy and kinetic energy equal. A by root 2. X equal to, we know, a sin omega t. This is the displacement equation. Velocity equal to dx by dt, which is a omega cos omega t, and acceleration equal to dv by dt. From this we get minus a omega square sin omega t. Now what is the graph of x, v and a in terms of t? What is the graph of this? So if to draw the graph, x equal to a sin omega t, graph will be this way. This is x equal to a sin omega t, so this graph is x. This is time, and this is x, a, v and a. Now displacement graph equal to this. Now velocity equation is a omega cos omega t. So a omega, here amplitude is a and omega is multiplied, so omega maybe this. So sin cos curve will be, if omega greater than 1, then this amplitude is greater than a. So this amplitude is at here, and this is amplitude a, and this is omega a. Amplitude of velocity is omega a. So the graph will be this way. Now this is the velocity graph. This will be the velocity graph, and the acceleration graph is minus a sin omega, again sine graph, but its amplitude minus negative start. So t equal to 0 negative. So this will be the sinusoidal graph, but negative side. So it may be like this way. And amplitude is period is same. So at same period, this will be negative. Now this is the acceleration graph. So because acceleration equal to minus sin omega t, so start from here, and this is sinusoidal graph. Period will be same. So this is the acceleration graph. Student, this is the end of the class for today. To get the part 2 of SHM, watch my another video. Okay, thank you.